So in this screencast, I want to talk about the meaning of a confidence interval. By now you're familiar with the mechanics and mathematics behind how you calculate one, but it's a little bit tough to interpret what it actually means, what you're actually doing. So for example, here we have an engineer that measures and records the temperature of boiling water, and he or she collects 5 different temperature measurements. And these 5 measurements constitute one sample. Don't confuse the number of measurements with the number of samples collected. So we collect those data, and you had 5 of them. The engineer reports, well, the 95% confidence interval for the mean water temperature is 97 plus or minus 6 degrees C. What does this plus or minus 6 degrees C mean? We might see it in a different form. Could be reported the 95% confidence interval for the mean water temperature ranges from 91 to 103 degrees C. Or you might see it the 95% UCL stands for the upper confidence limit for the water temperature is 103, or the 95% LCL is 91 degrees C. What we really want to get at is the true average, the true mean water temperature. We use the Greek letter mu to symbolize that. And if we knew that, we wouldn't need to do any of this confidence interval, because we already know the true mean water temperature. But unfortunately, we never get to know that value. One reason we don't know it exactly is because all measurement devices have some degree of uncertainty. In this case, it could be that the thermocouple, if you put it in cold water and then put it in hot water and then put it back in cold water, it might be that if it was a lousy thermocouple, it could be off by a few degrees. And that difference between measurements prohibits us from making a distinct or an exact measurement of the population mean. Another reason could be if we looked at the tank of water. Let's say that water was heated from below. We might expect a warm region of water at the bottom, and then everything above that is a little bit cooler. So it's important when you're taking temperature measurements of this vessel that you take your thermometer and measure temperatures over here, measure one up in here, another one at the bottom, kind of randomly over the place. So if you took 5 different measurements, you're going to be trying to take measurements at 5 random locations. And the true population mean for the water temperature is an average of an infinite number of measurements scattered randomly throughout the vessel. Obviously, we can't collect an infinite number of measurements, and it would also assume that our thermometer is perfect, that there's no variation whatsoever in the precision of our instrument. Neither of these things will be true. We can only capture, let's say you only had time to make 5 measurements, and you don't have a very expensive thermocouple, and that thermocouple has inherent uncertainty in its measurements. So these are all the reasons why you see these plus or minus values on different measurements, or if you see a range of measurements for the 95% confidence interval. But what does it mean? I mean, 95% of what? What is the significance of 95 even? And I'll tell you what it doesn't mean. It's a common misconception that it means that 95% of the measurements will fall between the range 91 degrees C to 103 degrees C, and that's not true at all. The best way I can come up with how to describe it is through a number of different simulations. But before we do that, for the technique that I'm using, and the technique that you probably started using, assumes that the population of all the measurements are normally distributed. So we'll be making that assumption throughout this screencast. And a normal distribution is this bell-shaped curve which you're familiar with. And if we're taking water temperature measurements, this side could be relatively hot, this side could be relatively cold. If we were doing something else, like measuring the strength of an object, we pull on it until it breaks, and this object over here might be strong, and on the left side these are weaker objects. And if they're normally distributed, the population mean would fall right here. But we don't ever get to know the population mean. All we get to know is if, in this case, we were breaking things, we might break something that's weak, something that's strong. We might grab, ideally, if it's normally distributed, we'll capture some more measurements over here. There's a possibility there might be one that was particularly strong off to the right. So here I've made a sample size of n equals 6. If you took these 6 measurements and averaged them, we would come up with the sample mean, and typically it's x over bar represents the sample mean. Note that the sample mean does not match the population mean. Ultimately, this is what we want. We can't ever get at it, but we can get close and make some estimates as to how close we are to the true population mean. The simulation I'll show will present a graph. There'll be a bell-shaped curve, and we'll find a number of different data points that were gathered randomly across this normal distribution. So the computer will choose, it'll choose numbers that are more concentrated towards the center, and we might see a few of them at the outlier. So in this case, I've got a sample size of 1, 2, 3, 4, 5, and n is equal to 6. And if we wanted to, we could collect a few more samples, and presumably we'd have a higher sample density out here. And in this case, n is equal to 11. But note that I only collected one sample. I collected a sample of 11 measurements. I did not take 11 samples. What my simulation will also show is a horizontal line that represents the true population mean. And remember, in reality, we don't get to know the population mean, we don't get to know the distribution. All we're left with when you do an experiment are these values, these 11 values, and from these we have to figure out what the true population mean might be. Here's the results of one run of my simulation, and what I've got in the horizontal line is the population mean mu, which we're after. I'm showing the bell-shaped curve, which in reality you don't get to know. And in my simulation, it picks random numbers that are more heavily concentrated towards the center of this curve. It can well pick points towards the top of it or at the bottom of it, but they're highly unlikely the further you move away from the population mean. And then what I've done is calculated the sample mean, x bar, and that's just the average of these three measurements. I've also plotted the 95% upper confidence limit and the 95% lower confidence limit. And this whole range from top to bottom is known as the 95% confidence interval. The reason these are all 95% instead of, say, 90% or 99% is because I chose a value of alpha of 0.05. And I've also opted to collect 3 measurements for each sample. So if I rerun this, I would collect 3 more samples, but they wouldn't be in the same location. They'll be randomly distributed over this normal distribution. So things are going to look different every time I run the simulation. And what I want you to pay attention to is the number of times that the confidence interval does not contain the population mean. What this means is when I run the simulation over and over again, 95% of the time the population mean will be within these error bars. One example might be, let's say we had a class of 100 students, and each student took 3 measurements, 1 sample, of materials that would pull apart, and you measure the force needed to pull the material apart. So strong material requires a large force, a weak material doesn't require much force at all. And in a pile of parts, if we were able to measure them, let's say we had 100,000 parts, and let's say we spent weeks measuring the breaking strength of all 100,000 parts, then we'd know the population mean. But unfortunately, it took us weeks to do that, and now we no longer have any parts to use because we broke all of them. Let's stick with this simulation. We can't break all the parts, we can't measure them all anyway. So it's a classroom environment, and each student collects a sample of 3 measurements. The 95% confidence interval is calculated by each student. So you go through the math you learned in class, calculate the 95% confidence interval. What this means is that on average, 5 students out of 100 will calculate a confidence interval that does not contain the true population mean. However, we'll never know who those students are. We'll never know who truly encompass the population mean or not, because nobody knows the true population mean. Here's the first run in my simulation, and I'm going to tally it. It'll show the number of runs that I've done at the bottom, and it'll report the number of times the confidence intervals were outside of the true population mean. So each run might be each student performing the experiment, collecting 3 measurements at a time. So this is student number 1. Student number 1 indeed encompassed mu. Here's student number 2, also included mu. Student number 3, 4, 5. Look what happened to student 5. This particular range we happened to sample on the upper end of the normal distribution. And in doing so, we got an estimate that did not include the true population mean. However, we don't ever get to know when this happens. We just have to take the math at face value that only, on average, 5 times out of 100 we're going to miss the population mean. So let's keep going with it. There's another instance. Look at the wide range of confidence intervals. Some of them are real wide, some real narrow. So another one missed back there. We're up to 3 of them outside of the confidence interval, a 4th one. And here, out of 100 runs, 100 different students, only 4 missed the confidence interval. Only 4 confidence intervals were outside of the true population mean. Now, it's not strictly true that there will always be 5 missing out of 100, but on average, if we ran 1,000, then we might collect something like 50 samples, or 49, or 52, or 53. On average, it'll be much closer to what we would expect, this 5% missing. Let's run some experiments now in which students collect 5 different measurements. They break 5 different parts. And in this case, we'll see alpha is still 0.05. And out of 20 parts, we would have expected one of them to miss, but none of them have yet. Student 40 missed one of them. We would expect by now that we'd miss 2. So we just haven't run enough experiments to find this 5%. It varies over time, but let's run it all the way up. We'll run 100 runs, so all 100 students taking a sample of 7 measurements each. Incidentally, compare the length of these confidence intervals to what we had done before when n was only equal to 3. The bigger the sample size, the tighter your error bars will be, but still, on average, 5% of those will miss the true population mean. And again, 4 out of 100 missed the true population mean. Well, let's say instead of collecting only 7 measurements, let's say, well, let's work really hard. We're going to get a really good handle on this situation, and we're going to collect 100 measurements. Here's an example. N is equal to 100, so you'd be there all day. You'd be there for a really long time breaking all these 100 parts. And note how the parts are clustered, the values are clustered near the population mean, and it's less likely on the outside of it. And the error bars tighten up quite a bit, and the sample mean begins to be more consistently closer to the population mean. As we keep running it, we again would expect 1 out of 20 to fall outside of the mean. So we didn't hit it yet. Oh, we got 1. We'd expect 2. Oh, there's 2. Got a few more. The student number's 80. There are 100 students, and this time there were 6 confidence intervals outside of the true population mean. And again, it's all random. It's just, on average, we'd expect about 5 out of 100 to miss it. So let's go back to something more realistic. We'll collect, N will collect 3 samples with the same value of alpha of 0.05. Look at how large these error bars tend to be. In general, they're fairly large with only 3 samples. Remember, the more samples you collect, the tighter the error bars and the less fluctuation you'll see with X bar, with the sample mean. So let's say now, well, alright, we've arbitrarily chosen alpha of 0.05, meaning that about 5 of them will miss the true population mean out of 100. Let's say we want to be more careful. We only want to miss 1 out of 100. So we'll set alpha equal to 0.01. So in essence, we're going to say, I want to be really sure that an interval almost always encompasses the true population mean. And when I run that, look what happens to the size of the error bars. They get gigantic. If we ran this 100 times, that one got a little bit closer. 100 times, we would only expect one of them to miss the true population mean. And these are so large, the error bars are so large at a 99% confidence interval that it's almost useless. We would tell somebody that, the parts can be either really strong or really weak, but we know the true mean is somewhere within that bounds, but it doesn't do us any good. If we wanted to, we could try alpha equal to 0.01. In that case, only 1 in 1,000 would miss it, and those error bars are even bigger and even more useless. So people have figured out that 95% is provides a nice compromise between the width of the intervals and the number of times that you actually miss the true population mean. Lastly, we could figure out, let's say, well, I only care if we miss it half the time. I like really tight error bars. It makes them look like I've got a better handle on the situation if our error bars are real small. So let's run it, instead of alpha of 0.01 or 0.05, let's run it at 0.5. And when I do that with alpha of 0.5, it means on average it's going to miss the true population mean half of the time. And look at how tight those error bars are. We'll continue running through this. Again, we've run 5 runs, only 2 out of the 5 runs have missed it. These error bars are too small to encompass the population mean at any given amount of time. So if we speed this up a bit, we've approached 50 runs, there's 25 of them that had missed the confidence interval. Half of them fell outside of the confidence interval. And lastly, if we want to be silly about this, let's do n equals 1,000. Here's n equals 1,000 with alpha equal to 0.05. Look at how close the sample mean is to the true population mean. Look at how tight these error bars are. And look at how the distribution of measurements, the wide majority of them are concentrated towards the center of the normal distribution. There's a few outliers, outlying data points really high and really low. This confidence interval does include, for this first run, or this first student who gathered 1,000 samples or gathered 1,000 measurements, did calculate a confidence interval that included the true population mean. Here's another one. Another one. Look at how tight the sample mean is. It doesn't fluctuate very much. It's always fairly close, but it still will miss. And as I keep going, we would expect, if I run this all the way up to the 100th student doing the same experiment, 5 out of those 100 students are likely to miss the true population mean in their confidence interval. And here we have 4 out of the 100 actually missed. But you'll notice that the sample mean really didn't fluctuate all that much. So when you're doing experiments and you're working with confidence intervals, just remember that the confidence interval does not represent the fraction of measurements that are outside of the confidence interval. It's a popular misconception. That's not true. If you want to say it, you say, well, if I ran this experiment, if I collected 3 or 5 or 7 samples in each experiment, the confidence interval that I'm calculating will not bracket the true population mean 5 times out of 100 if I've set alpha equal to 0.05. And you've got a couple of parameters to experiment with. The first one is the number of measurements you're going to take. That could be really time-consuming or really expensive if you're breaking things. And the other thing you have to think about is what value of alpha do you want to report? Do you want to report a small value of alpha that gives you a great deal of confidence that you've encompassed the true population mean? If you did so, your error bars would be really huge. If you wanted to do an alpha of 50%, for example, you'll have real tight error bars, but they're going to miss the population mean 50% of the time. In general, engineers and statisticians have said 5%, alpha equal to 0.05, is a nice happy median for representing error bars. And this is what you're doing when you report a 95% confidence interval.